After studying about elastic collision in one dimension, the next thing that we have to study is elastic collisions in two dimension. So in two dimension, before collision and after collisions, particles are not moving in the same straight line path, but they lie in the same plane. So that's why we call such collision as elastic collision in two dimension. So for such case, we consider a particle of mass m1 moving with velocity u1 along x-axis. So this is the particle of mass m1 moving with velocity u1 along x-axis, and it collide with another particle of mass m2 which is at rest, and after collision these two particles move with velocities v1 and v2, making angles theta 1 and theta 2 with the x-axis. So these velocities make angle theta 1 and theta 2 with x-axis after collision. Before collision the velocities were u1 and 0. This particle of mass m2 is at rest before collision. So the velocity that these particles have, means v1 and v2, after collision, it can be resolved into its rectangular components, v1 cos theta 1, v1 sin theta 1, and v2 cos theta 2, v2 sin theta 2. These are the rectangular components of velocities v1 and v2. Now after collision we are going to find the rectangular components of momentum, because the principle of conservation of momentum is valid in such type of collisions. So we are going to apply principle of conservation of momentum separately along x-axis as well as along y-axis. So first we are talking about rectangular components of momentum of mass m1. So after collision, the rectangular components of momentum of first particle, that means of mass m1, these are along x-axis and along y-axis. So along x-axis the value of the component of momentum will be m1 v1 cos theta 1, because velocity in this direction is v1 cos theta 1. So it is m1 v1 cos theta 1, and along y-axis it is m1 v1 sin theta 1, right? So these are the components of velocity and these are the components of momentum of mass m1 after collision along x and y axis. Now for mass m2, the component, these are rectangular component of momentum, again in two directions, along x-axis and along y-axis. So along x-axis it is m2 v2 cos theta 2, and along y-axis it is minus m2 v2 sin theta 2. Here negative sign shows that this momentum is in negative y direction, not in positive y direction. So minus m2 v2 sin theta 2 represents, here negative sign represents the direction of this component is along negative y-axis, not positive y-axis. So these are the components. Now we are going to apply law of conservation of linear momentum along x and y-axis. First by applying conservation of momentum along x-axis. So along x-axis it is the momentum before collision should be equal to momentum after collision. So along x-axis momentum before collision is because of this particle only, and it is equal to m1 u1. Before collision it is m1 u1, and after collision it is the sum of these two factors. Along x-axis the momentum after collision is the sum of these two factors. So the equation we get for x-axis is m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2 cos theta 2. This is equation number 1. Now the second thing is by applying conservation of momentum along y-axis. Now along y-axis, before collision the momentum is 0 because the motion is along x-axis. So there is no motion along y-axis. That means momentum before collision along y-axis was 0, but after collision it is the sum of these two components, right? The sum of these two components. So we have to add these with their signs. m1 v1 sine theta 1 minus m2 v2 sine theta 2. This is equation number 2. Also, in elastic collisions, kinetic energy is conserved. This is an elastic collision, and in such collisions kinetic energy is conserved. So before collision the kinetic energy was half m1 u1 square, and after collision it is half m1 v1 square plus half m2 v2 square. Since energy is a scalar quantity, so we are not splitting it into rectangular components. So this is equation number 3. Now by using these three equations, the quantities v1 v2 theta 1 theta 2 cannot be calculated. We have four unknown quantities here, that is v1 v2 theta 1 and theta 2. These are the four unknown quantities, and we have three equations right here. So these four unknown quantities cannot be calculated using these equations only. So by measuring one of the four unknown quantities experimentally, the value of the other three can be solved. So out of these four, one has to be calculated experimentally. For example, by experimental setup we have calculated theta 1, and after that we substitute the value of theta 1 in all the three equations. Then we have three equations and three unknown quantities, and that can be solved by using simple equation methods. So such type of collision is called elastic collision in 2D. Now there are some special cases for such collisions also. For example, glancing collision, and by glancing collision we mean that a collision such that theta 1 approximately is equal to 0 degree and theta 2 approximately is equal to 90 degree. Means after collision one of the particle move along almost the same straight path and the other one is perpendicular to it. So in such case, from equation number 1 and 2, if we substitute the values, we get u1 is equal to v1 and v2 is equal to 0, and kinetic energy of target particle, that is equal to half m2 v2 square, is also equal to 0. So such type of collision is called glancing collision, in which the incident particle doesn't lose any kinetic energy and is almost scattered undeflected. So such type of collision is called glancing collision. Second type of collision that we have is head-on collision, and by head-on collision we mean that theta 2 is equal to 0 degree, right? By head-on collision we mean that theta 2 is equal to 0 degree, means in such collision the target particle move in the direction of incident particle. They don't make any angle in between them. So theta 2 is equal to 0 degree, and if theta 2 is equal to 0 degree, there is no change in the equation of kinetic energy, but equation 1 and 2, if we substitute the value of theta 2 is equal to 0 degree, then equation 1 and 2 become m1 u1 is equal to m1 v1 cos theta 1 plus m2 v2, and 0 is equal to m1 v1 sine theta 1. So this is the case of head-on collision. Similarly, if we have the third case in which there is an elastic collision for two identical particles. If the two identical particles are colliding, that means their masses are same. m1 is equal to m2 is equal to m. We are considering it as m. Then in that case, by the conservation of kinetic energy for elastic collision, we can find in the equation third of kinetic energy conservation, we put m1 is equal to m2 is equal to m, then we get half m u1 square is equal to half m v1 square plus half m v2 square, or if we solve it we get u1 square is equal to v1 square plus v2 square. Also, by the conservation of linear momentum in vector form, I am not writing it in component form, we are writing it in vector form, we get m u1 vector is equal to m v1 vector plus m v2 vector, or u1 vector is equal to v1 vector plus v2 vector. So if we calculate u1 vector dot u1 vector here, we get its value v1 vector plus v2 vector dot v1 vector plus v2 vector, and by solving this dot product we get the answer u1 square is equal to v1 square plus v2 square plus 2 v1 dot v2, right, plus 2 v1 dot v2, but this value v1 square plus v2 square, this is equal to u1 square, so we can write it as u1 square is equal to u1 square plus 2 v1 dot v2, which implies 2 v1 dot v2 is equal to 0, or v1 dot v2 is equal to 0, and if the dot product is 0, it shows that the angle between v1 vector and v2 vector is 90 degree. This is the case for two identical particles. So that's all for the elastic collision in two dimensions, in which particles are not in the same straight line path after collision, but they lie in the same plane. So that's all for the video. For further videos, stay tuned and keep studying. Thank you.